So here we're going to try to solve the infamous monkey problem. What we have in this problem, we have a hunter, pictured right here, and he's got a dart gun. And he's going to take that dart gun and he's going to shoot this monkey to tranquilize it so he can take it to a zoo and he can live a better life. So this is a very smart monkey, and as soon as this monkey sees this hunter shoot, he actually starts dropping, starts to fall. Now the hunter is very smart too, and he knows that the monkey's going to do this, and we want to figure out exactly where he should aim so that he hits the monkey and can tranquilize it. Should he aim a little bit above, a little bit below, or directly at the monkey? Now we've watched Mythbusters before, so we know that all things fall with the same acceleration. We saw this with a bullet shot versus a bullet dropped. We're applying the same physics principle here. So we're going to start with the operating assumption that we are going to aim directly at the monkey. That means we can draw a picture. We can draw an arrow. This is going to represent the bullet going straight at the monkey. And he's going to be going, this bullet is going to be going at an angle. To do this, to break this up, we're going to break it up into a right triangle so we can do some math to prove that this is true, that this is actually all going to work. So I'm going to do the x-axis or horizontal axis in red, and we'll do the vertical axis in blue, and we can see I've drawn a nice little right triangle. And with that right triangle, we can determine the direction that I'm aiming to hit the monkey. That direction is going to be theta. And following some of your classmates, I'm going to label this triangle. So this triangle, the only thing I did to get here is to assume that I aim at the monkey. This is assuming that if I aim directly at the monkey, I will hit it. Many of you got to this result just by analyzing the physics involved. The bullet, right here, and the monkey both have the same acceleration, and what's going on in the x direction has no effect on the y. So if I aim directly at the monkey, the acceleration due to gravity is going to pull me down from my bullet or my tranquilizer dart at the exact same acceleration that the monkey falls. So I'm aiming directly at the monkey. That is the only assumption I've made to get this nice little triangle. And so I can actually use this triangle for something. I'm going to label some pieces of it. I'm going to label the hypotenuse as L. That means if I do that, that this horizontal distance, the distance from the hunter to where the monkey actually is, this x distance, I'm going to call that L cosine of theta. So this is right triangle trig. We should be very good at this by now. And I'm going to label the y position, the height of this monkey, and I'm going to label that y equal to L sine of theta. Again, I get to this just by doing a right triangle. And this particular triangle is just representing distances, and all my distances here are going to be relative to where my hunter is. This is my starting off point. This is my origin for my axes. And just to make our picture a little bit less crowded, I'm going to draw the velocity vectors for this bullet too, because we'll need to know how fast the bullet's going. So I'm going to draw a little velocity triangle over here towards the left-hand side of my hunter. So this is going to be a similar triangle. I could draw it in with the big triangle that I already have, but again, I don't want things to get too crowded. So I'm going to call this some initial velocity v initial, and that's going to comprise two components, my v initial in the x direction and a v initial in the y direction, and we still have our angle theta here. Again, from geometry, this triangle right here is a similar triangle to this, so the ratios are all the same. Okay? Good. Now that we have our picture and we have our drawing, we can start writing things down, writing down what we know. And what we're going to want to do is we're going to want to treat the bullet and the monkey separately. So we'll have a little bit of stuff for the bullet that we'll write down, and we'll have a little bit for the monkey that we're going to write down. And what we're going to want to do is we're going to separate things into the X direction for the bullet and the Y direction for the bullet, and do the same thing for the monkey. X direction for the monkey and Y direction for the monkey. It turns out the X direction for the monkey is going to be very, very simple. The X direction for the monkey, since it's in free fall, we don't really have to worry anything about the X direction. Relative to our initial position, the position of our hunter right here, we know that the monkey is a distance X away, so we could right away say that the X position of the monkey is L cosine of theta if we want, but we don't have to, not very important. The monkey himself is just going to fall straight down. His path is going to be directly downwards. So he doesn't actually travel at all in the horizontal direction, so we really don't need to worry much about any of this X direction stuff for the monkey, and he becomes a very, very easy problem. He's just in free fall. So we have a Y direction free fall problem here. And then we have our bullet. We can trace the path of our bullet or our dart gun, and our bullet isn't actually going to travel directly along this hypotenuse. Our bullet's going to arc, right? Gravity's going to act on it. So our bullet's going to come up, gravity's going to pull it down, and it's going to kind of arc down, and then hopefully it will tranquilize our monkey right here at this position, and everything will collide at x equals L cosine theta. So you have a good picture of what's going on, and you can rewind and refer back to this picture, but from now on, we're just going to concentrate on writing down equations for the x and y direction for the bullet, and in the y direction, our free fall for our monkey. So, alright, here we go. We have our picture up top, and we're going to start writing down everything we know about the bullet, everything that could be potentially useful. Now we have some change in position for the bullet, some change in x. So these are all the variables related to those four kinematic equations. The change in x is a final x position minus an initial x position. And if I look at my picture, my final position for my bullet, for my dart, is going to be right here at x equals L cosine theta. So I can write that down, L cosine of theta. And my initial position for my bullet is going to be at x equals 0. I start at my origin. So change in x is equal to L cosine of theta. I also have some initial velocity for my bullet in the x direction. And this is going to come from our similar triangle up top. V0 is my hypotenuse. My V0x is the adjacent side of that triangle. So my V initial x is going to have to be V initial of my bullet times the cosine of the angle, cosine of theta. Where again, we remember that angle theta is the exact angle I need so that I'm pointing directly at the monkey. That's the only assumption that I have in this entire problem. So I have V initial x is V0 cosine theta. This also tells me that V initial y is equal to V0 cosine of theta because of the fact that we get to ignore air resistance. So the acceleration, this should be V final in the x direction, is the same as V initial because AX is equal to 0. Because there's no acceleration in x direction in our projectile problems. And then finally, we come to the final variable of interest, which would be a delta t. And delta t, I don't know what that is. But if I look over here, I can see that I know delta x, I know v initial x, I know v final x, I know the acceleration in the x. So I know pretty much everything in the x direction except for this delta t. So I can use all of these equations that I know and find this time. And that's very useful because time is something that kind of moves between the x and y directions. Time is the same for the two directions. It's the only variable that's kind of useful for whichever direction you're moving in. So I pick a kinematic equation. I just happen to pick out this one. Change in x is equal to v initial times change in t. And since this is for the x direction, I'll go ahead and do v0x plus a 1/2 times acceleration in the x direction times change in t squared. And I can see right away this 1/2 ax delta t squared goes away because I plug in my wonderful little 0 acceleration in the x direction, so that all cancels out, and I find delta x is equal to v0x times delta t. And I can solve this equation for delta t to get delta t by itself. That means I'm going to divide both sides by v0x to get this delta t by itself and find that change in time is equal to change in x over the initial in the x direction. And if I come back over here to everything that I've solved for, all the things that I knew at the very beginning, I actually have some variables I can write down for this. I know what delta x is in terms of my angle theta, and I know what v0x is in terms of this angle theta. So I can write that down. I'm just going to plug in for my delta x and my v initial x, and I find L cosine of theta over v0 cosine of theta. Cosine up top, cosine on the bottom. My cosines cancel out, and I get a change in time that's going to be equal to L divided by v0. So that is the total time that this dart is in the air. And that time is going to be very useful because it describes the time that it's in the air for the x direction. It describes how long the dart is in the air in the y direction, going up and down. Describes the total time I'm arcing over, and it describes the total time that this monkey is falling. So change in time, very useful variable to get, very useful variable to know for any kind of projectile motion problem. So I've got my bullet or my dart in the x direction. I use that to find change in t. What do we do from here? Okay, so where do I go from here? Now we're going to do the bullet or the dart in the y direction. You notice we still have the same exact picture as before, and I've added one thing up to this top right-hand corner. I've added in our change in time because that applies for the entire problem, for any kind of piece that we might want to talk about. So I'm going to do change in y now. We need to know what's the change in y. What is the final height of this bullet? So that y, I can draw that into this picture. That's going to be this y right here. And I'm going to label it y of the bullet. That's going to be the final height of my bullet. I want to know what that change in y is. I don't know what that is at this point. My v initial in the y direction, well, I can come to my similar triangle over here on the left. V initial in the y direction is my blue. It's pointing up and down. It's on the opposite side from this angle. So my v initial in the y direction is going to be v initial times the sine of the angle. V final in the y direction, I don't know what that is because I have some acceleration in the y direction. I do know what that is. That acceleration is going to be negative 9.8 meters per second squared. And then I also know my change in time, because I just found that in the x direction. My change in time is going to be L divided by v0. And if I look at what things I know v0y, ay, and t, and there's a wonderful kinematic equation that I can use to find out what my desired quantity is. I can find this delta y by following change in y is equal to v initial in the y direction times change in t plus 1/2 a in the y direction times change in t squared. So my change in y is going to be equal to v initial y, I've written it down over here, is v initial times sine of theta. So I can just plug that in, v initial times sine of my angle times my change in time, which I already solved for. Change in time is L divided by V0. L divided by V0 plus a 1/2 times my A. My acceleration, my A, is negative 9.8 meters per second squared. So I plug that in, negative 9.8 times my change in time squared, L over V naught squared. So I can look at my equation, see if I can simplify it a little bit. My V naughts are going to cancel out, and I end up with a final change in Y position of change in Y is going to be equal to L times the sine of my angle. All I did here was rearrange this sine of theta times L. I just brought the L out front. Minus a 4.9 times L squared over V0 squared. I got that 4.9 by taking 9.8 times 1/2. So I now have a change in position for Y. This is the final height of my bullet. So that's this distance right here drawn on our little picture. That tiny little height is YB. Is change in YB our bullet height. Okay, where to go from here? So we found everything we can for the bullet. We use the x direction to find this change in time equal to L over V naught. That's going to be the change in time for every part of the problem, the time that the bullet or dart is in the air, in both the x direction and the y direction, and the time that this monkey is going to be falling down. We found the final height of the bullet, this YB, the change in Y position of the bullet. That's got to be equal to change in Y equals L sine theta minus 4.9 L squared over V naught squared. Now we can start writing things down for the monkey. And we know for the monkey, we want to concentrate on the Y direction because the monkey's just falling straight down. He's in free fall. So what do we know for the monkey? We need to find the change in Y for the monkey. What is his change in Y? How far does the monkey fall? I need to find, what else? V0Y. This is going to be the initial velocity of the monkey in the Y direction. And that's going to be 0, because he starts off just holding onto the branch and immediately lets go, so he starts with 0 velocity. We might need to know the final velocity for the monkey. Final velocity, we don't know what that is right now. Maybe we can figure it out. And finally, we know the acceleration of the monkey in the Y direction is going to be negative 9.8 meters per second squared. And last of all, we know the change in time for the monkey is equal to L over V naught. The same change in time that we found for the x direction. So that's the total time that the monkey's falling. So let's find the monkey's change in Y. We can do that using, by now, our favorite kinematic equation. Change in Y for the monkey, I'm going to go ahead and label it for the monkey, is equal to V naught in the Y direction times change in T plus 1/2 A times change in T squared. Now this V naught Y times change in T is going to go to 0 because our initial velocity of the monkey starts at 0. So that cancels out nicely. And we end up with change in Y for our monkey is equal to negative 4.9 times L over V naught squared. So L squared over V naught squared. And I have my change in Y. So I look at this change in Y for the monkey, and I compare it to the change in Y of the bullet, and I see that they're not the same. Now, does this mean that I didn't successfully hit my monkey? To figure this out, we need to go to one more picture, and we need to kind of redraw this situation. But we'll keep in mind the change in time, the change in Y monkey, and the change in Y of the bullet. These three things that we've derived entirely by just assuming that we're aiming at an angle directly at our monkey. So keep these three equations in mind. And let's draw another picture and see what it all means and how this all works out. Okay, believe it or not, we're almost done with this monkey problem. Here I've kind of blown up the monkey and the tree, and the monkey's falling, and his change in Y, the change in Y for the monkey, this negative 4.9 L squared over V naught squared, is this distance right here, from where he starts down to where, in theory, he intersects and collides with the bullet or the dart gun. So that's what the change in Y of the monkey is. The change in Y of the bullet is how far above the ground the bullet is when it presumably hits the monkey. So that's our YB. Now if I want to enforce that these things hit, then what I need to do is I don't need the change in Y of the monkey. I need to know how far the change in Y is, relative to the total height that the monkey started from. So that we'll label in dark blue is the total height that I start with. We'll call this Y total. And if this total height that I have, this total height of my monkey, minus this change in Y of the monkey, however far the monkey falls, ends up being equal to Y bullet. So if Y total minus Y monkey is equal to Y of the bullet, then that means that they're both at this exact same height at the exact same time, and they're going to collide. So what I need to do is compare YB to Y total minus Y monkey. And if we go back to our original picture, you will find a value for Y total. That value you're going to find is going to be equal to L sine of theta. You can look at your original right triangle and you'll see that. So you can just rewind the video a little bit and if you don't recall, or if you think I'm lying for some reason. So you have Y total is L sine theta minus Y monkey, which is 4.9 times L squared over V0 squared. So that's my Y monkey plugging in right there. And I can circle this answer. And now I compare it to my Y of bullet. If they're the same, then that means that the bullet or the dart and the monkey collide. And sure enough, these two are exactly the same thing. So I have successfully tranquilized my monkey. And that is the monkey hunter problem.